All right, cool. So this section is mostly focused on data generation, and there's a couple other tests and things like this. I think it's a big area. To be perfectly honest, it's relatively new in the data science field, where we're thinking about like how can we generate this data. We're only talking about the real like the basics at first to get you started of like, how do you even generate data? But right now it's a big thing. For example, you have all this information and you're using this to like say, well, okay, I love this data, but I love more data, right? We're data scientists. We want more data, and more data is good. And we want to say quality data too. We don't just want trash, right? Garbage is not going to help us at all. So there's techniques, that we can do to basically help us generate our data. And this is what's actually kind of interesting, is that if we have an idea of what our data already look like, so like what the situation is, we can start developing more synthetic data. And this can actually be really, really useful. A classic example right now is like self-driving cars. So you can only put in, so many miles on a car, and that takes time and effort, expenses. You have to have someone behind the wheel, you have to collect all this information. It can be a huge cumbersome thing. So it'd be great if we could somehow like speed that up, basically, of getting this extra data. So actually I was at a conference with Uber's ATG, so Advanced Technology Group. So they're the ones working with like the self-driving cars and stuff like that. And they were talking about all the ways they were like generating this new data from the self-driving car data they had. And it was really interesting because like we asked like, oh, like where's all this data coming from? And they're like, no, we have to generate it all ourselves. Like there isn't like a place we could really go to and get data and go from there. It was very much being like, we have our own, collection data systems. They drive cars around in cities, and then they take that data, and then they have to recreate, like from the data, other data sets, kind of like synthetic data. And it's actually a really interesting problem because obviously, what might be the problems if we try to generate our own data from the data we have? You guys might already think like if I told you, it's like, oh, I made this data from my data set, what might be the first thing you think like, is that legit? Yeah, so what problems might you have?
Variables you didn't account for.
Variables you didn't account for. So maybe you are missing some aspect of your data, right? Like, maybe you only collected, things that were very common, right? That's a big issue. Anything else that we can kind of think about from it too?
Doesn't actually reflect the population.
Doesn't actually reflect the population. Good, right? So that's kind of a similar attribute there too. One thing you might kind of realize too, if you only collect, depending on how you collect your data, if you're only collecting the same data points, those are all the data points you get, right? And so it's almost too perfect. And so you need some variation. You essentially need some noise, right? Data is random, and it's not that, you can think of like even pictures, right? Every picture is going to have a little bit of, noise, either static or just the fact that, maybe someone's like slight, hairs out of place or something like that. If you ever look at, have you guys ever looked at like generated human faces, like from computers, machine learning models? It made the rounds like a few months ago. But if you ever see something like that, they're usually called GANs, which we'll talk about in future modules. But generative adversarial networks, they'll generate, what's it called? They'll generate some things like you basically taught it. It's like, oh, for example, a human face, or here, generate some cats. Or one kind of fun one is like they'll generate like startups. Startup websites, which are kind of funny because they take a bunch of startups and they try to recreate that thing. Maybe I'll send out a link for like a list of these. But one thing you notice on their faces, for example, the way GANs work, and we'll talk about this in the future, like actually say like how this works. But basically you have two parts of the machine learning algorithm. One is basically to try to learn what makes, like say for faces, what makes a good human face. And then the other one, that's called like the discriminator. And the other one basically is meant to try your best to create a good face. And so at first it tries to create a good face, and obviously machine learning algorithm is very, very bad. And then the discriminator says, hey, like you suck. Like basically like, you're awful making these faces. And it says, try again, and says like, this. And so basically the discriminator tries to get better and better at like saying what things you suck at, essentially. And then this one's saying like, hey, I'm trying to get better and better and better. It's kind of sometimes it's like a student and a teacher, where like the teacher, it's not going to give you the same test over and over again. If you keep messing up on, let's say, your multiplication tables, like you mess up on fives, they're going to just keep testing you on the fives times tables. That's kind of like the discriminator is, right, for a GAN. So it's kind of like you practice the thing that you're really bad at. and basically eventually you'd get really good. Well, what's interesting about this is essentially it's generating its own data. And you can see a lot of these GANs, for example, for images, you can see that in particular, it's a really bad time with the edges. Like if you ever want to look at, like, as of right now, obviously we can get better and better, but these computer generated images from GANs, the quick way to like, check, you know, if it's from a GAN is usually on the edges. You will see that it's not quite right. Like it looks a little fuzzy and stuff like that. And that's because there's a lot of noise in there. Like usually because different color changes, or there's, you know, for example, like a little bit of hair that's like just sticking off to the side, shadows and stuff like that. That's one of the reasons why it has a tough time, because it doesn't know exactly how to do that random noise. So it turns out though, we can generate our own data with this extra noise, because if we have an idea of how it deviates from the norm, basically, we can generate this data. And we can actually go the other way too. We can use data, sample on it, and also basically heuristically, not heuristically, that's the wrong kind of word, but for example, we talk about t-test and like z-test, right? So usually we talk about t-test when we compare two samples. You can actually use sampling, basically resampling, which is kind of like generating your own data, and determine, what's it called? Determine like if this, you can basically determine your own p-value. And the way you do that essentially is by picking out a bunch of values from your sample, but many, many, many times. And basically it's kind of like doing a sample of your sample. That's kind of like I imagine it. And with that, you can actually get a lot of information from it. Okay, so there's a lot of real interesting things you can do. And going back to like the Uber with self-driving cars, what they were doing, you know, like they're using like some kind of LiDAR system, right? And they're detecting like little points and saying, oh, over there, you know, there's basically like you can think of the data points as like if there's an object there, and then determining what those objects are. Well, the problem is if that, this happens all the time when you generate data, if your data is too clean and perfect, is that the real life data is not going to match your actual data. And because synthetic data is so much easier to generate, if you're not careful, you might actually generate so much synthetic data that it overpowers any real life data. And then basically your system only knows, your machine learning algorithm only knows synthetic data, which turns out to be too clean. So that's why you always have to add this extra noise. And actually turns out to be the hard part of generating data is make sure you have enough noise. And there's actually a whole bunch of things we can talk about, which includes like Monte Carlo simulations and stuff like this, which we'll talk about today too. So anyway, that was kind of my intro to say like why this is important. And it's actually one of these parts that are continuously being developed, and people are trying to figure out the best ways to get data, because some data sets are just not very common, right? Okay, so I'm gonna go ahead and share my screen. There we go. Cool. And then you guys can all see my screen right now. Awesome. Cool. Oops. Sorry. I'm trying to make it so I can actually see you guys. If you guys give me thumbs up or look confused during the whole process. Yeah, I saw you, Matt. Okay, good. Thank you for practicing your thumbs up, you know, in case it's broken. All right, cool. So the first thing I want to talk about, in the curriculum, obviously, there's more than what I'm going to talk about, but I kind of want to show you guys some of the things that's going on, some of the little bit of code. So the first thing is like the data generation, which is, I think, the very part of the section or the curriculum itself. And so I just kind of, a lot of this comes directly from the curriculum. Like I literally just like copy parts of it and stuff like that. And that way you can kind of see what's similar to when you're going through it yourself. But basically our data generation, the reason why it's good is it's very, very quick. You can generate a lot of data over collecting it, obviously, right? And then in our future, when we actually do machine learning models, okay, machine learning methods, algorithms, and stuff like that, for our next module and module 4, it's really useful to test out these parts. So for example, I kind of mentioned the opposite of like when you're doing data generation, you might be not getting the population, but that might also be true when you sample the population and get your own data, right? Like think of like the classic survey example. If you send out a survey to people, what's the big issue when you send out a survey? Is it representative when you get that information? What might be some issues with a survey and data collection? What kind of people respond to surveys?
Usually only filled out by people who do stuff online.
Yeah, so if you do an online survey, you have to assume that they're going to be online. Okay, they have access to that, right? So one thing, is like, oh, for example, if someone doesn't have access, this was a big deal when they talked about phone surveys before computers. If you did a phone survey, they loved it because people would answer the phone, but then also it meant that some people didn't have phones because their income, maybe didn't have a high enough income where it made sense for them to have a phone. So not everyone had a landline phone. Nowadays, what they try to call landline phone, I mean, almost like there's a lot of people. I never bought a landline phone myself, and there's a certain demographic who are starting to do that. The other issue too is at the time, this like you think like 70s, people started getting call screening, and the people who had call screening tended to be wealthier in that case. And so a lot of people would screen their calls and say, oh, well, I'm not going to answer that phone call, whatever it is, because I don't know who they are. So you get bias in those surveys too. There's also a bias in a lot of surveys. Think of like, Yelp or reviews. They usually tend to be all very positive or all very negative. You don't usually say, oh, I got this cool product from Amazon and say, oh, it was okay, 3. Like no one really does that too much. Like only, I mean, no offense if you did this, but like only weirdos do that. Like who's putting all these reviews out there saying, oh, this was okay, and like doing a long review? No, they usually say, if you read those reviews, they're like, oh, this is amazing, this is awesome. Or they say, this sucks, this company didn't do anything. So you get a bias in that sense too. So this is like data collection by itself might be biased in that way. So it's useful to actually generate your own data to say, hey, like, well, what does it look like if we have what we likely think is the distribution? Okay. And then also you can test for weird stuff too. For example, if certain aspects of data might be kind of rare, you can test and see how robust your model is. Okay. Now, remember that we want to try to make it realistic. We want to make it random. We don't make it too random, right? Otherwise, there's no point of actually generating this data. But we want to try to get that nice, feel. And this honestly is kind of like, it feels very ad hoc, being like, oh, what's random enough? And this comes from practice of saying, looking at other data and say, what does our data actually look like? What's the likelihood of the randomness built into it? Is it a normal distribution? And usually we try to go for a normal distribution, but sometimes you can go for distributions that are kind of strange. So here's a few examples, and this is taken mostly from the curriculum. I just made this function here because the code along makes you do it over and over again. And I was just like, oh, this just makes sense to do a function. But basically, I'm just going to do it so I can do some plots. So for example, I'm put these colors, red, blue, green. I'm going to put an extra one right here. This is just a dictionary, so then I can easily, what's it called? Oops, 3. Let's do, what's yellow? In case I want to put another one. Okay. So basically, this is a function, so I can plot the data. I'm getting some x values, some y values. It's going to be on a scatter plot. Okay, and making it into a data frame so it's easier to kind of process into, so we can plot it really easily. And then this is just so we can group it by a label. So if there's a certain label that we have, for example, this data down here that we're going to basically make with blobs and basically points. Basically, it's collect all the blue points, all the green points, all the red points. In this case, the labels are going to be 0, 1, 2, and then if I put a third one, like 3, right? So anyway, and then just making the plot right here. So pretty basic stuff. So this is not so much new things. But this right here, sklearn dataset sample generator. This is what sklearn, if we kind of seen a little bit of this, right? Sklearn. It's a really useful, what's it called? Useful for a lot of ML models, okay, to build a lot of things. So we can actually build our own data sets. We can build our own like generation from this package. So sklearn is pretty robust. It's got a lot of different stuff. So one thing is just making blobs, which kind of you can kind of guess what that's going to look like based on the picture. And basically, it's just making a blob of this data. And so I run this now, and it should get a slightly different picture. You see right here, it just basically said, all right, this cluster, let's say 0, this red on the bottom right. All right, basically have those points randomly put them there. There's a bunch of other features you can do for make blobs. For example, random state or what the centers are. So you can actually say where you want the centers to be. So if you know for your data, for example, it's going to be centered around these 3 points and then make them randomized, you can do that. This is a great way to also test out, say, oh, if my data is clustered, is my algorithm going to be able to detect these clusters? So when we do classification, for example. And then I believe I can actually put in something like this too. Let's try, oops, let's try 4. Okay, so in this case right here, I have 4 different centers right here going through. I think I can even go down to 2. Let's see. Yeah, so then you can see this part. I put this 4th one so I can have that yellow. But so anyway, And then obviously features is just saying, you know, how many things you can put in there. So you can kind of like randomize, and you can see I can keep running this over and over again, right? And you can see the sample should be different. Oh, well, I have to run this part over and this one. So you can see you can get generated data this way. Okay, cool. So this is pretty common when you want to do classification. Okay. Now this one right here, this one's like moons, and this is actually a really tricky data set because depending on what you're doing, for example, we'll do other machine learning methods. Some models have a hard time with these parts where it crosses over. And you should think about this. I'm kind of like looking ahead for module 3, module 4, supervised learning, which we kind of talked about last time with ML models. Basically it's classification. You're trying to draw lines around or draw groups around areas. So you can think of this being like, you know, let's say identify, I'm trying to make something up on the fly, but like identify if it's a male or female based on whatever data comes in. And the idea is like, you know, you would have these like labeled already, oh, these are all male, these are all female. And then your machine learning model says, okay, I have a new point like right here where my cursor is. Like, it's like, is that a male or female? And how, you know, basically what is going to be. And so this is how you can kind of generate this extra data. So you can kind of see, I can generate this part. Note that I can change this noise too. For example, I think I can just go up to like 2. And you can see that it can get really messy. So obviously it's like, oh, that's really like, at this point, not really a moon shape and stuff like that. So again, that's why you kind of want to say, what's the right amount of noise that you want to put in? So you can see here, there we go. You can see like, it's like where like, if you knew it was a moon shape, you're like, oh, I can kind of see what's going on. It's above and below, but obviously it's very noisy. Usually about 0.1 is around what it is. And again, there's more options in here. For example, I can't read this random state, but you can set off a random state so you can get the same value every single time. So if you want to test that algorithm over and over on the same randomized generated data, you can do that. Okay. So again, moon shapes are really useful. Next one we have are these circles. And these are actually really useful for Gaussian distributions because Gaussian distributions tend to have these like circular parts basically around the mean. And so again, just the same idea, you can see that. And a lot of this, like especially these two are especially good for supervised learning. This will also get in there, but it's going to be different Gaussian distributions from the last section that we just went over in the curriculum. We'll go over that. And then of course we have our good old regression lines, right? So this is kind of nice, is that I can make a lot of noise on this part. So you can see noise right here. And that's obviously it's supposed to be along this line, but we can kind of like make it fluctuate and stuff like that. In fact, we can, if we give it now, let's say like 1,000 data points, and I'm going to adjust this alpha. So this alpha, just to get, you know, is a way to, it basically change the opacity. So that way I can see the points. If I just set alpha to 1, which is the default, you'll see it's really hard to see. So I can actually adjust it to like 0.01. So you get an idea of what that looks like. 0.1 might be too far. But you can start getting like, okay, it's clustered all around here, but you get that line. And you can see I can put in more noise. Let's see. I don't know how much noise I can actually put in before it looks too random. So there we go. Okay, 15 noise. I actually don't know what this number represents specifically. I'm sure it says in the documentation what this noise actually means, but you can see all these different features right here of what you can do. Okay, obviously you can put multiple features, but then of course you got a multi-dimensional graph. So it's kind of hard to actually, you know, plot that out and show you guys, but you could basically make data with multiple, what's it called? With multiple features. I believe you can just go like this. Let's just see if this works. I haven't tried this out before. No, okay, never mind. So again, more documentation, read that through. Oh, I know why. If we change this to 2 now, X, it's getting saved into X, I believe. Okay, I'll let you guys play around with that and check out the documentation a little bit. But just note that you can adjust how many features are and then basically plot out each feature itself. Okay, cool. So anyway, regression line. So what's nice now is that I kind of mentioned this before, like in module 1 when we talked about regression, linear regression. Linear regression is like, cool, you can do that. But what if your function is not in a linear side? You can kind of think of it in 2 ways. You can either adjust your model to make that data, let's say it's parabolic, right? Parabolic, where it's like this little, like, you know, like y equals x squared. We can either think of changing the model so it fits into a parabola, or what we can think of, we can change the data to fit this model. So if you want to do the opposite, when you want to generate data that is more parabolic, because that's what your data is supposed to look like, or you want to test your model against this kind of thing, you can basically use the same thing with make regression, but just modify it with these values, basically your own function. So in this case, we're just squaring it. We're basically just taking the cube of it, right? So basically we can make these different values and we can kind of get a general idea. So this is like, oh, if this is, what's it called? More parabolic, data set versus more of third root, or not third root, third power of it, basically. You can even do more complicated things, like if you wanted to do something, I don't think Python supports that. But if I want to do something like log, which I think won't work because there's a 0 in there, but worth a shot. Oh. Yeah, you get the point. I'm not going to import this right now, but you get the point. You can change this around and do basically modify your data to fit something that's closer to like what you modify your generated data to fit something that's closer to like what you're looking at. Okay. So any questions on how this all works or anything like that, or any questions? Seems pretty straightforward, right? Okay. Again, 100 is kind of small, but you can kind of get the point of saying like, oh, you can make more and more data. And this allows you to quickly test your algorithms. Usually the reason why you're generating this specific data is you want to see how well your algorithm fights against some of these methods. Some ML models and algorithms do better on certain kinds of data over other ones. So this is a great way to just quickly just like throw just junk, not junk, but like throw differing kind of data sets and see how well it does. Okay, cool. All right, so.
Quick question,
yeah,
sorry to interrupt you. When you're choosing a number of samples, like if you are actually going to be generating data, how would you pick that number? Like, would 500 be enough, or what is?
Yeah, it all depends exactly what you're trying to achieve. So with an ML model, you don't need that much data. If you're trying to train a model, the more data you have, the better, which might be like 1,000 is probably not enough. But if you want to test saying like, hey, if I give like I'm kind of giving, what's it called? These labels, but you could give basically to kind of test out your model. So we kind of think of like the ML model. We only did, we haven't done ML too much yet, but and ML means machine learning if you guys haven't caught that. But when we do the training part, we basically have a large amount of data, okay? And these are kind of crude ways, like you could train on this part. In that case, you might want to put, these data points are pretty straightforward, depending how noisy it is. Like you probably could train an ML model pretty decently on this amount of data. But obviously if it's more noisy, more realistic, you need more and more. But the idea is you probably do your training on your, with some real data, and then maybe you augment that by adding more and more. And you have to start thinking about other things like the variances that it'll create and stuff like that. And for example, if I have like 10,000 data points, there's a good chance that some of my data points will be completely off from like the rest of the data. And that's because just pure chance, right? That's like realistic. But anyway, usually what you would do for this kind of stuff, because there's more advanced ways you could generate data, you would take your training data that's realistic, train your model, and then you would test it against this kind of stuff. So what you'd be like, to say, I said an example, like saying it's male or female. Let's say male is like blue, female is red, okay? Is that you can then say, okay, given this point, and I'm gonna say this is going to be male, and you feed that point in there, okay? And this should hopefully match close to like your realistic data. You feed that point into there and say, does it give it male? Does it give it female? And instead, of course, getting this one point, we can just do all of them at once. And basically, you're testing your accuracy. So again, basically it's coming down to the fact that it's like, what if we give them a distribution that looks kind of strange? Okay. That's
gotcha. Good. Thanks.
No problem. All right. So yeah, this is more like augmenting. Like if you just obviously trained against this purely, there has to be something that gives you a reason to want to train against it. All right. So this kind of goes into resampling methods. So I kind of said like, oh, we can generate this data. And resampling methods, it's kind of like you already have the data and you want to basically use that data. Maybe it's not enough like as your classic points, or maybe it's really difficult, for example, to get the parametric values. So remember when we talked about different ways we can get our probability density function, we can use parameters. We can use parametric, basically. Like we know what the population mu is or the population standard deviation is, right? And a lot of times we don't necessarily know these values. We might have an idea and we can use those kind of things, but sometimes we don't really know. So resampling methods allow us to actually do this thing called permutation tests. And basically it's kind of like, yeah, the way I kind of think of it is like you're taking samples of samples. And so it's kind of an alternative to our parameter distributions where we know what the data should look like, what the population should look like. We're not really sure what what the distribution should actually appear like, but we can use the sample that we already collected and try to infer from that on what the population is. So we've actually done this before. It's with the central limit theorem. So central limit theorem, we basically say, okay, cool. We have, what's it called? We have a sample, but we probably know is if we took multiple samples from the population, we would eventually get a normal distribution, right? That's the central limit theorem, essentially, right? So what we kind of do is say, well, okay, we have that same idea, but instead of sampling across the population, because we don't have all that data, we don't have the data that was basically collected already, we can sample within that data and basically do that multiple times, doing groups of those samples and compare those samples together and see, basically you can kind of think of it like this is the whole population, this is our sample, and now we're sampling within that sample, and we're doing multiple samples. In fact, we might do like 1,000 or 10,000 different samples and compare all of those and see how likely those things differ from each other. And we can actually do our testing from there. Okay, and that's actually, we can do this for like our p-value and the variation. So this is actually in one of the labs that you will do in this section. I think it's the resampling methods lab, where you actually will try to determine the p-value by basically taking samples, basically subsamples of all these, of a big sample, and basically try to determine from there. Because the t-test in a lot of ways kind of determines that it's like, oh, it's like an alternative essentially. And a lot of reasons why we do that is if it's just difficult to, determine those parameters. So it's a good option in that case. And it works out mostly because of central limit theorem. It's like if we take many, many samples of our sample, we can get a good picture of what the population is. Okay. Any questions on that? It's kind of meta. Like it's kind of like, oh, you're taking samples of samples. But one example I guess I can say about it is like, imagine we have two different, like I think the curriculum has two different samples, and I can't remember. I think it's like blood tests or something like that. But like, let's say we have a population or a sample. We'll call it sample mean. So the sample mean mu A, which isn't quite right, but whatever. That's what the curriculum does. Mu B, right? And basically we can say, okay, what's the difference between these different these means, right? And this is how we can do it like a t-test, right? A two-sample t-test. And we can compare these difference, say, okay, there's a difference in this part. Well, we can do this with the full samples we have, sample A, sample B, but we could also, instead of trying to figure out from there and say, oh, the population doing a full t-test, we can instead say, okay, let me take a subsample from here, from A, and a subsample from here, and then compare those means, right? These little subsample means, and then see what this little difference, or this, like, I'll call it sub, and what that sub is. So like that's like one subsample, like I put randomly basically from mu A and one subsample from mu B, compare those differences, and this will give me some value. And then I just say, okay, let me do that again for another subsample. So like if you imagine if this is all of mu A, I might say it's like, okay, this is my first subsample. And just note that depending what method you do, you can like have crossovers, but I'm just gonna run it. And then like, it's like, okay, this is my second subsample, okay? And so then I do the same thing over here. Oh, this is my first subsample, and this is my second subsample from mu B. Well, now we can compare four different ones, right? We can compare this one and this one, this one and this one, this one and this one, this one and this one. And we can see those differences. And we can do this basically thousands of times, right? Depending how big our data is. And from this small sample set, we can hopefully determine, okay, how many times basically does our hypothesis testing hold? Like, for example, let's say our hypothesis test is that mu A minus mu B is greater than 0. So basically there is basically mu A is bigger than mu B, right, in the sample or in the population. And we basically, that's our like our alternative hypothesis, right? What would be our null? Does anyone know what our null would be in this case for a two sample? I'll give you a hint. It's everything like this. and then 0 on this side. What symbol do we put here for our null hypothesis, if this is our alternative? What was that, Maiden?
So,
You say equal?
yeah.
Okay, cool. Yeah, and that's right. So basically you're saying, okay, that's our equal, right? So basically you would say, all right, let me see how many times we can reject the null hypothesis using these subsamples. And then basically if the majority of times are over this subsample, if the majority of these like subsample comparisons is basically passes, so we can reject the null hypothesis, then we can reject the null hypothesis as a whole group, saying, well, basically we're kind of doing a little probability within that group. Okay, it's I think it's a little strange at first, but basically you can think of it as like samples of samples. So like you're almost treating like the big population. Instead of this big population, you kind of treat it within this little population. But the way you kind of fix with that is the central limit theorem by basically taking many, many samples. Cool. Any questions on that?
So what happens after you take many, many samples of samples? Do you not get a similar result to what you would find if you had just operated on the original samples?
I'm sorry, Matan, you're like kind of breaking a little bit, like in between words. I didn't quite catch that, didn't you?
Can you hear me now?
That's great.
I'm sorry about that. So let's say, all right, so you're repeating that process over and over 1,000 times, 10,000 times, and looking at the delta between the subsamples. Would you not eventually just reach the same conclusion that the original samples would have given you?
Right, and that's the kind of the way. That's a good question. Thank you. So one of the issues is saying, okay, like if you were doing this like for every single sample, like wouldn't we just get the same thing? And this actually comes into now. I kind of skipped over ahead to permutation tests versus all these parts. Basically, bootstrapping and Jackknife. Basically, there are ways we sample, and basically it helps us prevent to basically keep the same variance. If this makes sense, it basically allows us to avoid doing that exact thing. And you can actually do this mathematically. Kind of fun fact, when I was prepping for this lesson, I was kind of searching, like, oh, someone have a good example of bootstrapping versus Jackknife. And I searched, and basically the first thing that came up was a forum on like stats page. And they actually linked to the first upvoted comment on there was a paper from my physics professor back in Santa Cruz, who basically, he was computational physics. He specialized in Monte Carlo simulations. But it's kind of funny. I was like, oh, like that's going through. But basically, there's a lot of math that kind of goes into this. I guess I could share you guys that. Let's see here. What was it? Jackknife, jackboot. Yeah, so I'll show you guys this paper. Oh, I have this still stuff on here. Yeah, so you can see right here that he actually does a full comparison of like what the bias is and stuff like this, to correct bias. So this actually goes through the whole mathematics of saying like, oh, why can we do this? How does this represent? In physics, we have this bar right here that just means the average, like their mean, right? So you can kind of go through this part a little bit and go through it, but you can see very math intensive. And you can actually prove this stuff. We don't do this whole thing through the curriculum because, to be honestly, like it's quite a lot of math going through, but it's a good thing to kind of read through. Remembering back to like when he was instructing, when I was one of his students, he was very smart, but there was also many things just like, whoa, that is a lot to take in. It took a few hours, if not days, to kind of absorb and say, okay, like that's what's going on. So if you're curious, this is what you would look at of like why these things can work out. But just know mathematically we can actually do these things and say, oh, they actually do approach what we would expect in the population versus the actual sample. But good point. Okay. Hopefully I answered your question a little bit, Matan. I kind of sidestep by saying, just look at this math, but you can always check it out. So bootstrapping and Jackknife, which is one of our two different ways of sampling methods. Jackknife is actually one of the more common ones. It's basically non-memory intensive. So essentially it does a few things. One is that it's non-memory intensive because we basically can just like sample along the same sample. We don't have to do operations over and over and over again. This is important for back in the day when computers were much slower. Like again, talking back, Professor Young. When he would do this stuff, he wouldn't use Python at all. I remember doing this. He said Python's way too slow. He had to like use C, C++. Like that was like faster. He said maybe Java, but Java's not that great. Like that's kind of like the level he was doing. But computers now are getting so much faster, it's kind of like less of a deal. But if you have very, very large data sets, you can imagine if you had to like reshuffle everything every single time as you do basically to get your sample, it can be very memory intensive. So Jackknife allows you not to have to worry about that. Basically all you do, it's going to sound really simple, is basically you take, like there's more general M jackknives, but for example, just a single jackknife, which is what the curriculum talks about. You basically have your sample, like your whole list of all your numbers, right? All your data, and you just basically like pick one out and then say, okay, that's my sample after you pick one out. And then you move along and say, pick out the next one. Like, so you take the same sample, pick out the next one. That's my new sample. And so basically you just remove one element in the data set. And that's basically your subsamples now. And it's kind of interesting that like when I first heard this, I'm like, how does that even work? Like, it seems like you not like have the things that you want. Like it just seems a little too simple, but it turns out the mathematics work out where you basically are doing this enough times where you're getting the same variance and stuff. What's nice about it, people really like, is that especially for papers, it's what's it called? It's the same thing over and over again because you're not doing randomly. You are literally I shouldn't say random samples. I don't know. I put that in there. It should be samples. It's not doing it randomly. It's taking out elements in there, so you can repeat the same process as long as you have the same data sample. So it's kind of nice to be able to do that test over and over again and know that you just haven't had a weird thing. Again, this is kind of more of the older method, but it's still very useful. And then we have bootstrapping, which is probably closer to like what I think most people kind of would picture for this. Is you basically do random samples with replacement. So basically you have your whole sample and you essentially pick out values from your sample, okay? So like if you had like, let's say the numbers, I'll just write it down because that's probably easier than me trying to gesture at you guys. But like, let's say we have samples like sort of 1, 2, 2, 3, and then like 4, something like that. When we do bootstrapping, you say, okay, I want a sample of 1, 2, 3, 4, 5. So a length of 5, okay? So actually I won't write that because it's kind of confusing. But basically like, oh, okay, I want 5 spots, okay, in my subsample. And so you randomly go through it, usually uniformly, but you randomly go through it and say, okay, randomly pick, oh, 2, okay, cool. And then you go randomly go through it, oh, 3, okay, cool. Okay, randomly go through it, oh, 3 again. Okay, randomly go through it, 1, okay. And then randomly go through it, oh, 2 again. So you do that. Basically, it's like you keep going through it, you're randomly picking out a data sample from this part. So this is more memory intensive, obviously, because you have to kind of like essentially every single time you're picking out a single data point, you have to randomly go through it, pick that one out, and then do it again for the next one. So it can take a lot more memory, especially if a very large sample. And then you just repeat this process. So this is your one subsample. And then you do the same thing to get another subsample. Compared to Jackknife, Jackknife basically says, okay, my first sample is 1, 2, 3, 4. My next one is 1, 2, 2, 4. Okay, like that's kind of like what Jackknife is basically. You're basically subcycling it, taking one remove. You can do M Jackknife, which allows you to move multiple ones. Now this, obviously you're gonna look at this like, this is really small. like why would I do this? And basically it comes down to like, if you have very large data sets or it's very difficult for you to actually process it all. This is actually why Jackknife was really useful for, what's it called, back in the day when computing resources just could not fit all the data you had. All right. So those are the two resampling methods that curriculum particularly talks about. And the most common ones, I actually don't, to be honest, I don't think I could tell you another resampling method off the top of my head. I'd have to look it up because these are so common, bootstrapping and Jackknife. Okay. Any questions about this? Okay, cool. To be honest, if you're really curious about it, say like, like how'd this work? The research, like that's what you should do. And what's interesting enough is, at least this is my background, with computational physics, with statistical mechanics. I find that like, that's the stuff that kind of like led a lot of, like, it was basically data science before data science was a real big thing. So it's kind of useful to see like what the mathematics they have in there. Okay, cool. So this is our resampling. I showed you data generation on here. Oops. Mouse, there we go. So good to have. I'll make sure to push this up on GitHub too on that main page. I haven't done it yet because I was kind of editing a few things, but very great stuff. Most of the stuff's in the curriculum. Next one I think is really interesting is Monte Carlo, which is again part of the thing. And Monte Carlo, does anyone know Monte Carlo? Like when I say Monte Carlo, like the place, right? Yeah, you can think of it like, oh, it's like Las Vegas. And it's kind of funny is that I remember like, again, Professor Young, he kind of joked is that, you know, if Monte Carlo was discovered in the by a US citizen, we would have called it Las Vegas simulations versus Monte Carlo simulations. Basically, it's just the idea is that we use random iteration to predict values, okay? And so it's kind of nice is that the reason why we do these things is one of the reasons why is like if your data is very, very large, right? It might not make sense to process all of it through. Now, this is becoming less and less of a thing that we kind of talk about because when we talked about large was like, oh, we don't have the computational power, but computing power now is getting better and better. But even then, there's always going to be more data and more things you can do with this than you can like physically process, right? You can always generate more data, and we're generating more and more. So Monte Carlos are actually very useful to get part of what's the value. There's also these things called Monte Carlo integration. I don't know if you guys have ever heard that before. So if you ever go back into calculus, there was always this joke, like I remember in physics, they say, we give you all the easy integrals that you can solve by hand, or like, you know, you can actually solve. But most integrals and stuff like this, most mathematical methods are not solvable. So we can actually use they would use Monte Carlo, for example, to basically try to figure out an integral. And if you ever think of an integral in calculus, so derivative, what's the derivative kind of like related to when I talk about like a line and stuff like that? If I said derivative, hopefully a certain word popped in your head. Hopefully it's slope. So you can think of derivative is slope, right? It's an instantaneous rate of change, right? That's all derivatives are. So an integral, does anyone know what like the kind of like converse, but like what the related thing would be for an integral? Yeah, it's fun. Bring back math to you guys, right? So yeah, so you can kind of think like this guy right here, this function, this funky function, okay? We have like our derivative, right, would be our slope, our instantaneous change right here. So our integral, remember how it goes from like A to like B? Okay, our integral. Really that means it's just area underneath the curve, AOC. Okay, so it turns out a lot of integrals, you can't really solve it easily. You can't solve it in its analytical form. Basically, you can't write it down in a mathematical equation. You kind of say, this is the integral, you know, and it turns out a lot of integrals are like this. You're just like, but I don't know what the value is, like something. And you can do certain methods. You can do mathematical methods. Like, it's a bigger than this, but smaller than this kind of deal. And basically, computation with especially computer science, they said, hey, let's just basically try to figure it out. And so Monte Carlo integration basically uses the same method. So if you're curious, if you come across that too, it can show you some methods of like how Monte Carlo is used. But the main thing is basically is that we're just going to randomly pick out some stuff and see how it goes. And the way I like to imagine it, it's a lot of times it's like you're trying to look, it's really useful if you think of areas. That's where like Monte Carlo integration is. So like one, for example, we'll show this in a second, is that there's this picture right here. And basically we're going to end up trying to find the value of pi based on this picture, okay? And you can kind of think like, okay, well, how would you find pi from this? Well, you know, and this is where it's a little creative. You say, okay, well, if I know this is the radius right here, I know this is basically the square right here, I can say, what's the area of the whole square? What's the area of a circle? Subtract that out and say, oh, there's pi hidden in there. And basically we can use the formula to figure out, saying, hey, like, what is that pi? So this is like something like in Pi Day, like about a month ago, people would like all freak out and be like, oh, we can calculate pi this way. And I don't know. I'm more of a tau person if anyone wants to know. But you guys don't want to know, so it's okay. But anyway, the main thing is that we're basically having something that usually you can represent it like as an area. And I have to imagine like you're throwing darts. So like you imagine like I'm a really bad dart player and I just throw random this junk out there, right? I just take one dart and throw it out there. And sometimes I hit in the middle, but most likely I'm hitting just somewhere random, okay? It's uniformly random. And basically from this, we can actually say, okay, how many points are actually outside of the circle? How many points are within the circle? And we can actually say, because it's random in that case, we can actually figure out what the value of this pi is from randomness, okay? And that's kind of like the whole idea of Monte Carlo is you use randomness to try to figure out these parts. And the reason why we do this is because there's other methods you can do, but Monte Carlo can be really powerful because you don't need as many points to get a decent value. Actually, this is what I had used in my my bachelor's thesis for physics, is that I used a Monte Carlo simulation of basically these different particles and interacting with each other. And it turns out it was just, you could try to computationally make these things, but if even after like 128 values, it would make a normal computer just like slow down a ridiculous amount. So you can do Monte Carlo, say, well, let me just update this one, and then update this one, and update this one, and update this one. And you would do this many different times over and over again. And that would actually give you a pretty decent, like it gave enough randomness, but also gave enough value at the same time. So it's a good balance in this way. And you'll see many Monte Carlo simulations written exactly like this in these for loops. So that's kind of like how you kind of approach it. So this is kind of like the motivation from where Monte Carlo comes from. So anyway, that's kind of like the big thing I wanted to say. I could go more into Monte Carlo, but there's actually this really great article I've come across from Monte Carlo, and it kind of explains a few ways you can kind of like approach Monte Carlo. So one, he kind of explains, I thought it was kind of funny. He basically talks about this guy who's drunk and he just randomly walks throughout the room, and basically it's like, what are the chances that he'll randomly get to the restroom within enough time? And so you can actually, like, he's like, okay, like, you know, play the scenario. And basically you can say, oh, he randomly moves in directions, either up, down, left, right, all that stuff. And you basically run the simulation, say, okay, let me go ahead. He has at most 50 steps. If he takes more than 50 steps, he's never going to find that bathroom, or he didn't find it in time. Okay. If he runs into like a wall or like a table, it's like, oh, then we'll stop. You know, like basically he didn't make it there. So you can run this over and over again. And so it's like you run it one time and then you do it multiple times and over and over and over again. And basically you can take the whole percentage and say, oh, how often does he actually get to the bathroom? And you're like, it's kind of funny. The author even goes like, well, cool. Like, that's really interesting, but why should I care? And basically he compares, it's like, well, a big thing we can do is basically like, for example, 538, when we do election predictions, you know, basically they run simulations of saying, based on what polls they have, what data they have, saying, well, how likely is this? But because there's always some standard deviation, some margin of error, you know, it might vary. Like even though they're polls, they say, oh, like say 60% Democrat, 40% Republican for the candidate for this area. There's always a little deviation from there, right? So basically they can do that and essentially run these Monte Carlo simulations of basically like thousands of elections over and over and see how many of them actually go through. And you can see what the likelihood of a certain candidate winning for an election. Another one that talks about is sports results. Again, kind of similar is that, you know, you can kind of think of saying everyone's got a little bit of, you know, randomness in their thing, and you can actually start seeing like how likely something would happen. So sports results. Another one, weather prediction. Weather is great because weather is one of those things where like it's a very chaotic system, which ends up being more random as you go over time. And you can actually start doing some stuff. For example, there's so much information from weather. There's no way you can get every single data point, but you can basically track very large areas randomly in that sense and basically reduce the computation significantly to at least get a decent picture. Obviously, as you probably noticed, the weather prediction is not perfect. A lot of times, you know, we can't get more than 7 days, and even those 7 days are not super accurate. So anyway, that's kind of like the deal. And he has a part 2 as well, where he talks about using a simulation for like modeling a poker. Yeah, I think it's a blackjack game, or maybe it's a poker game. But he basically talks about this. So I would read this through. It's a nice, easy read, as you can tell. Like, it's not like there's any huge math in there. If you want to take a little break from like all the math, you know, coding stuff, it kind of helps you kind of get a good picture of it. But anyway, and it's being used a lot in a lot of these new systems when you're trying to generate data. Basically, you're trying to simulate things that happened already. Okay. So cool. Any questions about Monte Carlo? Okay, cool. All right, so that kind of finishes up. Note the curriculum also has a first part where we have, oh shoot, KS tests. I always forget how to pronounce that. It's like Russian. Like my pronunciations are awful, as you guys probably have noticed by now. But there are parts of that too. But Monte Carlo, data generation, I think these are really important stuff that we don't, there's a lot of new stuff coming out. And I think the best thing to do is like kind of do some research and see what's out there. And then of course, in the curriculum itself, there are some links to some extra resources as well. And I'll send this out to you guys right now, since who knows when I'll update it quick enough. Okay. Yep. Well, you have to actually copy it, Victor. Oh, I did copy it. Okay. Just 3 times. All right. I'll go ahead and stop the recording then and stop sharing.